Hello, this is Mrs. Dowell, and I would like to spend some time today talking with you about translations. This is a section in Module 4 and in Module 3 that oftentimes gives students a lot of difficulty. So I just want to kind of go through some of the basic translations with you so that when you see them, you're not ultimately confused and shut down. There are 4 translations that are presented to you here in the lesson, in the modules. There are really only 3 of them that we use on a regular basis at this level. When you get into higher math classes beyond Algebra 2, you will use this translation right here a little bit more frequently. But as for Algebra 2, you need to be aware of this translation, and this translation. Now, what's so cool about these translations is that these things are true no matter what type of a function it is that you are using. Whether you're using a parabola, which looks like this, or whether you are using a trigonometric function, cosine of theta, looks like something like that, whether you are using a polynomial, y equals x to the 4th, which is sort of W-shaped, whether you're using an odd function, an odd-powered polynomial, which looks kind of S-shaped like that. So these translations are true for all types of functions. Even this is one that you might not have seen, an absolute value of x, which is V-shaped. Okay, so translations, it is good to be familiar with these different types of translations because they are used across the board with any type of function. This type of a translation is going to shift your graph, shift the graph left or right. Okay. This type of translation, number 2 right here, this is called a vertical translation. It's a vertical shift. This will move your graph up or down along the y-axis. And you will see, we will study each one of these individually. And then this third translation down here is so important because it reveals 2 things to us. Whatever the sign of A is, whether it is positive or negative, that will tell us something about the graph, as well as the size or the value of A. That will tell us something about the graph. Now, if you will notice, and again, I don't want to downplay the importance of this type of a translation right here, but if you will notice, this and this have a very similar affects the width of the graph, affects the width of the graph. So this is the first translation. This is the one that deals with the horizontal shift, which means the left and the right. Okay, the left and the right. Left and right movements. And these graphs are just generated from Desmos, and these are graphs that you would see in Module 3. We will get to the Module 4 graphs momentarily, but these are the types of graphs that you would see in Module 3. All of these graphs are quadratic. That means that the highest power is equal to 2. So I'm going to say highest degree equals 2. And you can see that is true here. Highest degree equals 2 in each one of these. So these are all quadratic. When graphed, they graph a parabola. And in each one of these cases, For simplicity's sake, there is no plus k tacked on to the end. So what I want to do is give you a general kind of an idea up here. Y equals a, x minus h plus k. Now what goes right here could be squared, or it could be cubed, or it could be to the fourth power. So again, there's one common theme that is true whenever you are dealing with translations. You've got this this general y equals a x minus h raised to some kind of a power plus k. That power determines whether it is going to be an even powered polynomial or an odd powered polynomial, and that determines a great difference in the graph, because even polynomials, if that was a 2 or a 4, even polynomials will end up going in the same direction. Odd polynomials will end up going in opposite directions. So what I want to look at specifically here is this, and let's examine. This one, y equals x squared, is often referred to as the parent function, which means that it is the function that we compare all of the other functions against. Okay, it's the mama bear. It's your basic function with, and I'll put that in the form that you're accustomed to seeing it, which is y equals 1 x minus 0 squared plus 0. So you can see that the a value is 1, and the h value is 0, and the k value is 0. And that's why it is this red one right here in the middle with its vertex at the origin. Okay, so I should write that. Vertex is at the origin, and the value of a is 1. That's positive, so that means that the parabola is opening up. Now, in each one of these examples, the a value is 1. Also, in each one of these examples, the k value is 0, plus 0, plus 0, plus 0. That's why they all have a y coordinate that is on the x-axis. Okay, so again, the h in the equation determines whether it is shifted left or right. Okay, so one thing that I need to point out to you is let's take a look at the parent function, which is this red one right here, and I will try, at risk of life and limb, I will try to imitate the parabola so that I can show you. I'm going to move this parabola around. Okay. This parabola is the same as all of these other parabolas. If I could just simply take this pink line that I just drew and slide it in this direction, all of the ordered pairs would just simply have been moved. This is 3 units. This is the point 3. So here's 1, 2, 3. All of the ordered pairs of this parabola are just simply moved, translated 3 units to the left. Okay, be aware that that is the blue equation. So the vertex of this parabola is -3, 0. -3, 0. So you may be looking at the equation going, that says +3, but the vertex is -3. So I would like to explain to you why that is the case. In our general formula, it simply says x minus that doesn't change. In this case of the blue parabola that I'm looking at right here, the h value is -3. The h value is the x-coordinate of the vertex. H equals x-coordinate of the vertex. Okay, be aware of that. K, on the other hand, represents the y-coordinate. Okay, so K is the y-coordinate. All right, so if the x-coordinate of this vertex right here is -3, and I was just going to plug in the h value right here into my equation up here, I would have x minus -3. And that, we all know that minus a negative becomes plus a positive. That is how this right here is a positive. All right, now let's take a look at the this orange graph over here, where its vertex is 2, 0. So we're looking at this equation right here. The vertex is +2, 0. Notice that the vertex has simply been translated 2 units to the right. And so my h value in this example is 2. And so therefore, when plugging it in, it would have been x minus, because that is part of the formula, x minus, and then the h value would be 2. So it is interesting, and I must point this out to you, that when you see x plus 3 in parentheses, when it is in parentheses, it is actually moving, translating, shifting in the opposite direction of what you may think. You may think that x plus 3 should move the graph 3 units to the right, but instead it moves it 3 units to the left for this very reason up here that I just explained. 3 units to the left. Okay, so I'm going to go back a page and clear all this jazz out. Come back and want to identify for you each one of these. Again, the red graph has an origin, has a vertex of 0, 0, 0, 0. And the blue graph over here has a vertex of -3, 0. And the green graph way over here has a vertex of +4, 0. Notice x minus 4, because the h value is actually 4. And then the orange graph has a vertex of 2, 0. And then the light blue graph has a vertex of 1, 1/2, 0. This right here is 1. Okay, so you can see that it was translated 1/2 of a block to the right. So the vertex here would be 0.50. Okay, and again, where is all of that coming from? That is coming from this general formula that deals with translations. Again, I would like to identify for you on each one of these, the h value is -3, sorry. The h value is 0.5. The h value is +2, and the h value is +4. And that is why over here there is only one graph that was shifted to the left, and that's why this is a +3. So hopefully you can identify that whenever your expression is in parentheses, that is a horizontal shift left or right. a horizontal shift left or right. And we describe it by saying, let's look at this orange graph or the green graph over here. We would say that parabola has been translated 4 units to the right. X minus h. 4 units to the right. Okay? Okay. So now let's take a look at the k value. Well, once again, we're going to continue. We are going to continue to examine this generalized formula, y equals a, x minus h, in this case again, squared plus k. This is our transformation function. Transformation function. And all parts of this transformation function can be changed, including this highest degree, which we will get to that shortly. Okay, so here's my parent function with my vertex of 0, 0. Notice the k value here is -2, and that's the blue graph. So it was translated down 2 units. And the red graph was translated up 2 units. I think it is important for me to point out to you that this says -2, it was translated down 2. This says +2, it was translated up 2. So all 3 of these graphs are exactly the same. They have just been simply translated up or translated down. Now, why is that so different from the previous example? And the reason has to deal with this plus k right here. The plus k, as opposed to the minus h. Okay, the plus k just simply means that whatever is tacked on to the end of your function, it's just going to demonstrate its movement. So if a -2 is tacked on, that means it was translated down 2 units. If a +2 is tacked on, that means it was translated up 2 units. Okay? So again, that's why you've got this f of x plus this number that's tacked on out here, which describes for you which direction it goes, whether it goes up or down. Not too difficult, not much else to it than that. All right, now we've got to examine this a. And I've been very specific in the choices that I've picked out here because the a value, as we learned back at the very beginning, the a value affects whether or not it has been reflected across the x-axis right here. So if a is negative, then you're looking at reflections, not opening up, but opening down, okay, if a is negative. Now, the size of a determines whether it is wide or very skinny. See, wide or very skinny. See, this isn't hard. You're getting the hang of this. Okay, so the a value, what does the a value do? A affects the width of the graph and possible vertical and horizontal shifts. A negative a will reflect the graph over the x-axis. All right, so in this case, I want to point out to you, whoops, going in the wrong direction. In this case, I want to point out to you that a is equal to 1, a is equal to 2, a is equal to 4, and a is equal to 1/2. Okay, so let me just show you something that is fascinating, in my opinion. I call A the rate of change value. The rate of change value. Now, rate of change actually means slope, except for the fact that we are not dealing with linear functions. We're dealing with parabolas, and later on we're going to be dealing with cubic functions. So I use A to represent the rate of change. In other words, let's examine the most extreme, which actually the most extreme that we're going to be able to see on the graph is the blue graph. Okay, so here's one. Notice that if A is 2, from the vertex, I went over 1, as I always do every time, and I went up 1, 2. This is the point 1, 2. This is the point 1, 1. This is the point 1, 1/2. I can't see the black one, it's off the screen, but if I had extended the graph up, it would be on this axis of 1, it would have been at the point 1, 4. All right, now why is that significant to us? That tells us that if we are able to identify where our vertex is, which in each one of these cases, the vertex is at the origin, okay? So in other words, I'm looking at multiple different examples of this, x minus 0 squared plus 0, where the only thing that's being affected is the A value. A is 1, 2, 3, 4, or 1/2, okay? So that's what I'm looking at. That's why they all have a vertex at the origin. But if the A value is positive, they all open up, and it also tells me what is the general rate of change when you are examining right around the vertex of the parabola. Now, recall that if you were graphing a line, you would need 2 points to graph a line, but 3 points does make it easier to graph. Well, when graphing a parabola, you do need to have 2 points, but 3 points is nice to have. So in this case, we always will have our vertex. We will know how far from the vertex to go based upon this A value, always over 1. And then it will either be up 1, up 2, up 4, up 1/2, or if each one of these is negative, it would be down 1, down 2, down 4, down 1/2. Okay, now that only gives us 2 points, which is a little misleading. It makes it feel like that these are linear equations, which they are not. You have to remember that every one of these parabolas has an axis of symmetry, okay? An AOS, an axis of symmetry, which runs directly through the origin. In this case, it runs through the origin. The axis of symmetry actually runs through the vertex. So since the vertex in each one of these cases was 0, 0, our axis of symmetry is going to run through 0, 0. So what that means, just quite simply, is that if this point right here is located 1/2 of a unit to the right of the axis of symmetry, then there is a mirror reflection located 1/2 to the left over here. Okay, so I don't want to get too much into that because that's really graphing parabolas, and at this point you should know, and that doesn't really discuss translations. But you can always use the rate of change value, which is the first value after the vertex to the right. If you go over 1, then that number right there will tell you how far up you're supposed to go. And then you can graph the mirror reflection over here, and that would give you 3 points, and then you would be able to graph it pretty easily. Another thing that is significant for you to notice here, and I'm glad I labeled it here, A is 1/2, A is 1, A is 2, and for the black, A is equal to 4. In case you haven't noticed, as A gets bigger or increases, as A increases, your parabola gets skinny. Your parabola gets skinny. So the wider the A, the smaller the A, the wider the parabola. So if I had an A value of 1/4, that would mean I would go over 1, and I would go up 1/4 of a unit, which would be approximately here in the middle. This would have an A value of 1/4. Okay? Approximately here in the middle. 1, 2, 3, 4, 5. Yeah, they divide it into 5. So at 2.5, that would be 1/4. Okay? All right, so hopefully that's helpful to you. Here we go. Now I've got a nice mixture. Once again, I need to point out to you that the vertex for each one of these, the vertex is 0, 0. The only variation between these parabolas is what is the A value. And you need to see this because we said there were 2 things that A affected. It affected the width of the graph, and it also affected its minimums or maximums. So if A is positive, it opens up. So I'm looking at this one opens up, this one opens down, this one opens down, this one opens up, and this one opens up. Okay, so that is very helpful to us. And so we can see, and the same thing applies here. Let's take a look at the green graph. Our vertex is 0, 0. If I go to the right one, according to my A value, A is equal to -3. That's my rate of change value. According to that value, I'm going to go to the right one and 1, 2, down 3. I know about the axis of symmetry, and so I know there's another point over there. The blue one, I wasn't able to get that one on the graph. Oh, yes, I was. I'm sorry. If I go over 1 and down 1, that means my A value is -1. Vertex 0, 0, which means that the equation here would be -1 x minus 0 squared plus 0. So you're actually able to write the equations of these graphs just by examining what the vertex is and what that A value is, whether or not they're opening up or whether they're opening down. So without looking at the equations, I'm going to examine this red graph right here. I notice that this red graph right here goes to the right one and up 1. Well, that would simply mean that my A value is equal to 1. Or my vertex is 0, 0. So if I was going to write the equation for the red graph, it would be y equals +1 x minus 0 squared plus 0. If I was going to write the equation for the blue graph, I went to the right one and up 2. So for the blue graph, A is equal to +2. And hopefully you're confirming that over here. So if I was going to write the equation for the blue graph, it would be y equals 2x minus 0 squared plus 0. What's the deal with the orange graph? If you go over to the right and go up, it is right in the middle of 0 and 1, which means 1/2. That means A is equal to 1/2. Okay, so it's kind of like the slope, but not really. It only works for the very first point to the right of the graph, meaning 1 unit away from the vertex. All right, so let's continue. Now we start getting into, these are cubic functions, okay? Cubic functions, which means that the highest degree is 3. Although the transformation function still remains the same, it is simply that the highest power is 3. So the k value simply translates up or down. As you can see, the red graph it's not called a vertex, it's called an intercept, because a vertex only pertains to a parabola. That's the only one that has a vertex. But it's called a y-intercept, so you can see that the y-intercept here is 0, 0, and you can see that the k value is 0. It did not translate up or down. For the blue graph, you can see that the k value is +2, so it translated up 2 units. For the green graph, you can see that it is -2, so it translated down 2 units. All right, so you may be saying, whoa, this looks really different than what I was thinking. Well, that is true, because this is why. Y equals x squared is parabolic. Y equals x cubed is cubic. Okay, so the thing I need to point out to you here is that when the highest power is even, your graph is going to end up going in the same direction, up, up. When the highest power is odd, your graph ends up going in different directions, down on the left, up on the right. That is referred to as the end behavior. The end behavior. For each one of these, the end behavior is down/up. Down on the left, up on the right. And that's the difference between a cubic function and a squared function. All right, let's move on. Now we're looking at the horizontal shift. Again, we're looking at the number inside of the parentheses to determine, is it going to be the same? Is it going to be the opposite? So, if we look at this, y equals x to the third. By the way, these parentheses are not necessary right here, but what you can see is that in the transformation function, a is equal to 1, so I have 1 times x minus 0 cubed, plus 0. Okay, and this point right here is often referred to as the turning point, okay? The turning point. So, if you're going to translate your graph 1, 2, 3 units to the left, then the h value is -3, which would mean that in our transformation function, the h value would be -3. So that would be x minus -3. That's why when we're looking at this blue graph, it is x plus 3. This is a transformation of 3 units to the left. And this, without even looking at a graph, although it's there for us to view, would be a transformation of 3 units to the right. H value equals 3. K value is 0. You can see that. All right, moving right along. Now I've got a mixture, once again, and the thing that you need to understand is that when the A value is negative, it reflects it across the axis. Okay, so let's see if we can focus here on this red graph. That's our parent function. Oops. The red graph is our parent function. Okay, the turning point for the parent function is 0, 0. It's not called a vertex. Again, it's called a turning point. The turning point for the red graph is 0, 0. Some other things that I want to point out to you are that these graphs will go through the point 1, 1 and the point -1, -1. So this is the smooth curve that is created by the parent function. Now, A in this case is 2, which simply means that instead of going over 1, up 1, you're going to be going over 1, up 2. And of course, it's off the graph. But you can see it over here. Over 1, 2. Okay. So I have to stress to you the difference between the blue graph and the green graph. This A is -2. Okay. Turning point 0, 0. And then over 1, up 2, over 1, down 2, like this. I'm probably just going to have to draw it right here. Y equals 2x to the third is a down up graph, whereas y equals -2x to the third, paying close attention to the green, would be considered an up down graph. So the end behavior for this would be down / up. The end behavior for this would be up / down. All right, and then I include the orange on here as the A value is 10, just to indicate that the higher the A value, the skinnier it will get. The higher the A value, the skinnier it will get. Remember, the red curve here is the gold standard. This red curve here is the one curve that we compare all of the others against. So if A is greater than 1, it's going to be more narrow. And it would be nice if you could just block everything out and focus only on the orange graph where it's 10. I can assure you that if I went over 1, I would go all the way up to the point 110. Okay. So, and then of course the black graph is just the reflection in the opposite direction. So the orange graph has an end behavior of down, up, and the black graph has an end behavior of up, down. Okay, next slide. So what I've got here is a mixture of all of these different types of translations. And my hope is that you would be able to examine the important key features of each of these graphs and be able to pair it up with the matching graphs equation. Okay? All right. So I'm scanning down here and I'm looking to see, remember, all of these are going to have some form of the transformation function in it. The points that have been identified to you here on the screen are the turning points. That's where they go, they turn and go from the down to the up, or they go from the up to the down. A vertex is also a turning point. It goes down, hits that vertex, and then begins going up. Okay. The end behavior, however, is different for a parabola. Up, up. Okay. All right. So here's your parent function. A equals 1, turning point of 0, 0. So I'm going to go with this graph right here in the middle, which is so familiar. Be aware that this is at 2, which means that this point right here is 1. A little hard to make out. This point is 1. So I'm going to say that the parent graph, I'm going to label this graph as number 1. This will be number 1. Okay. Now, I'm going to look at this one. The K value is 4, which means that this is simply a translation of the parent function up 4 units. So imagine taking this graph that we just examined, that I labeled as number 1, and sliding it, not changing any of its width or anything like that, just sliding it up 4 units. And again, if you will notice, if I go over 1, I'm still going to be going up 1. The same thing is true on the left side. If I go to the left 1, I'm going to be going down 1. Okay, so those are your 3 points right there that you would use to help you graph this. Okay, so I'm going to label this graph up here as number 2. So this is number 2. All right, now let's examine this graph right here. I'm going to label this graph as number 3, and we've got to go find it. Again, the A value is 1. The H value is -2. And the K value is 0. The turning point would be -2, 0. Just by looking at the equation, the turning point would be -2, 0, because my H value is -2. Well, now I can just come over here and kind of look for which one of these graphs has a turning point of -2, 0. So I can see that this one right here is exactly the same as the red one, just translated 2 units to the left. This is a translation of 2 to the left. So I'm going to label this green graph as graph number 3. Whoops. Okay. Okay. So if I recognize that the h value is -2 here, because this simply said x plus 2, well, that would mean that in this case, the h value would be 4, and the k value would be 0, because it would be plus 0. All right, so the h value is 4, the k value is 0, and my a value is -1. Okay, recall that our parent function goes down, up. This is when a is equal to 1. That means that if a is -1, then our function is going to be going up, down. So I need to be looking for a graph that goes up, down, and I need to be looking for a translation of 4 units to the right. So my turning point right here of 4, 0, and if you will see, this is up, down. Okay, so this one I will label as number 4, ironically, 4. Okay, and so now what have we not observed? We have not observed lastly, by the process of elimination, this blue graph right here. So let's see if we can understand. This is an up, down, up, down. So what does that mean? If it's up, down, that means that the a value is going to be negative. Up, down has a negative a value. Down, up has a positive a value. So I can see that this is up, down, and I can see that this was translated 2 units down. It was not translated to the left or to the right at all. So this x minus h part right here, h is 0. I mean, when you're looking at your turning point, you can just look and see h is 0, k is -2. In fact, that is true for every one of these graphs. H is 4, k is 0. H is 0, k is 4. So in this example, if h is 0 and k is -2, and I know that this is an up-down, then I know that if I go to the right 1 and down 1, that my a value will be -1. So I'm looking over here, and I can see the -2 translated down 2 units. There is no set of parentheses because there was no horizontal shift at all, simply a vertical shift. So this was shifted. This is called a vertical shift. A vertical shift down 2. And then this negative is what gave me the clue for it to be an up, down. All right. Now, as we progress throughout Algebra 2, we will be looking at all different kinds of polynomial equations as well as trigonometric equations. They will all use the transformation function. We didn't look so much at linear equations, but you could very easily put this into y equals mx plus b form and see a very similar transformation that a would kind of represent your m. It is referred to as the rate of change. Okay? All right, I hope this has been helpful to you. If you have any further questions, please contact me, and I appreciate your time.